This is the 35th lecture of the course MTH 204A for section B. Recall that in the last lecture we will talk towards the end we were talking about algebraic elements in an extension of fields, and the definition was this, that in an extension of fields alpha is said to be algebraic over the bottom field k if it satisfies. So here we have 4 statements and all of them will be equivalent. The equivalence is yet to be proved completely. So if alpha satisfies one of these conditions, then we will say that alpha is algebraic over k. So in the last lecture we proved that so 1 to 2 we have established. In fact we have also shown that this f is unique. So therefore henceforth we will call this f as the minimal polynomial of alpha over k. So by definition minimal polynomial of an algebraic element over the bottom field is the unique irreducible monic polynomial which has alpha as a root. Okay. Now the third condition that also we have proved, that from 2 to 3, that also we have proved that this will be automatically a vector space over the field k, and this vector space is dimension finite. And then we also proved the fourth statement in that list, which we have proved is that alpha is contained in an extension. So I mean the situation is there is an intermediate extension, there is an intermediate extension E. So E is a field intermediate extension such that we would this dimension E over k is finite. Also recall that for any extension of fields, let's say E over f. So if f when viewed as a vector space over E, if this is finite dimensional, then this dimension is also called the degree of the extension, and we denote this by this notation. So in view of this terminology we call it a finite extension. What it means is an extension which is finite dimensional over the field k. So we prove 1 to 2, 2 to 3, 3 to 4, and 4 to 1 is yet to be proved. So 4 to 1 that actually follows from a more general observation which we should record as a proposition, follows from so this just says that every finite dimensional extension. So let me make it much more formal. Suppose we have an extension E over f is a finite extension, that is the degree is finite. Then every alpha in f is algebraic over E. So why this is true? The proof is very simple, that given alpha we will look at this set. So all non-negative powers of alpha, certainly this set cannot be linearly independent because the dimension of the vector space f over E is finite. So therefore there will be a linear combination with coefficients coming from E, such the linear combination of the powers of alpha with coefficients coming from E, which will be 0, and that exactly yields the polynomial. Okay. So this part, so this 4 implies that follows from a more general observation which says that every finite extension is algebraic. So what I mean by this, whenever I say an extension is algebraic, that means every element of the top field will be algebraic over the bottom field. Okay. So these 4 statements, and also there is another one in terms of determinant, but I deliberately skip that because that is not going to be of that is not going to be of much help to us in this regard. So So these are the statements, the equivalent versions of an element being algebraic. So you see these are these statements are these are the analogues of the these are the analogues of the corresponding statements in case of integral dependence. Okay. So these are their field versions. Okay. So since we have this equivalent, we have this analogous equivalent statements in case of field extensions. So therefore it is reasonable to expect the analogues of the consequences of such statements in case of integral dependence as well. So that's exactly the scenario here. So the corollary of this is we obtain that suppose k over f, so sometimes instead of writing this we also write L over k, but however you should not confuse that with quotient space, because certainly that does not make any sense here. Okay, so suppose L over k is a finite is an extension of field, and alpha 1 up to alpha n belonging to L are algebraic over k, then k, the minimum subfield, the smallest subfield of L that contains both k and these elements, is a finite extension of k. So how to prove this? The proof also goes exactly along the same line to that of integral dependence. So what you can do is simply that you can rather use this product rule. That suppose you are given a tower of a series two successive extensions E over k and k over L, and both are finite extensions. Then from this you can prove that L over E is also a finite extension. How to prove that? The way is simple, that suppose in case of k over L, suppose V1 to VL is the basis, and for this case suppose W1 up to Wm is a basis. Therefore from that you can show. So there are several ways of doing that. V1 Vi Wj, this forms a basis of L over E, and now when this is there, you can directly apply it to this case from k to k alpha 1, and then k alpha 1 alpha 2. Certainly since alpha 2 is algebraic over, so since alpha 2 is algebraic over k, so then alpha 2 will of course be algebraic over this field. So therefore this is a finite extension, and step by step it goes like this. Okay. So by this product rule of successive extensions, you can conclude that this is also a finite extension. And further corollary to this would be the following. So okay, so I can simply erase that as well. So again, so you see these results, they follow, exactly along the same line of that of integral extensions or the integral dependence. So the further corollary to this would be that given an extension of fields, we collect all the elements which are algebraic over k. So this is a field this is a field over, this is a subfield of this is a subfield of L. Okay. So, how to show that? That is exactly simple. So, if you take two elements x and y which are both algebraic over K, then x plus y will be contained in this finite degree extension. Okay, x plus y will be contained in this finite degree extension, and since both are algebraic over K, so both similarly x y. So, thus therefore, both of them will be algebraic over K, and the existence of inverse is also quite obvious. So, therefore, because x is contained like an element x is contained inside kx, which is in the case of an algebraic element, this is a field. So, of course, x has inverse. So, yeah. So, given an extension of field, set of all elements in the top field which are algebraic over the bottom field, therefore, a subfield of C. Okay. All right, I think now I should give some examples. So, like as I said that you can immediately see these are the results that follow, these are the the natural analogues of those results of integral dependence in the context of field extensions. So, we do have let me give you some examples. So, for example, if I take K to be Q, then of course K to be Q, and let us say E to be L to be C, or perhaps any subfield of C, then these are the elements of these are the examples of algebraic elements. First of all, any integer, and furthermore any rational number in fact. So, the difference is in case of integral dependence, no rational number was integral over z unless it is an integer, but certainly in case of fields that is not the case. So, any rational number is of course, in any extension of fields, all the elements lying in the bottom field are of course algebraic over the bottom field, any rational number. Then of course we do have these things root 2, root 3. So, all this algebraic integers. So, in fact at this point the following is a very interesting observation which I may leave to you as an exercise. So, you see that whatever we have mentioned so far, already many of them are already seen to be algebraic integers. So, the question here is that what is the if in an extension of Q. So, if we take an algebraic integer, is it going to be an algebraic number? Is it okay? So, before that I think I should give this definition as well, because it is easier to use this. So, a complex number which is algebraic over Q are called algebraic number, is called an algebraic number. So, this is the analog of algebraic integer. So, the thing is maybe I should leave it exercise. So, suppose alpha is an algebraic integer, that is integral over z, it satisfies a monic polynomial with integral coefficients. Alpha is an algebraic integer, of course that will imply alpha is an algebraic number. Then the converse converse certainly does not hold, because 1 by 2 is an algebraic number, not an algebraic integer. But however, here something more is true. So, alpha is an algebraic integer, so that means there exists an integral polynomial with monic polynomial such that, so gx such that, so this is monic polynomial, of course degree greater than 1. So monic polynomial such that g alpha is 0, okay, and since alpha is an algebraic number, so we have f alpha is the irreducible polynomial having coefficients over this. So now what we do is f alpha has coefficients over q. Now we can immediately like clear out the denominators and then take out the GCD of the coefficients of f alpha to arrive at a, let us say f alpha, so let us use some different notation, maybe f alpha dash. So f alpha dash alpha will also be 0 and f alpha dash is now a polynomial over zx. This is of course primitive, okay. And the way we, so what we have done is we have multiplied f alpha by some non-zero constant, so that doesn't, so this f alpha prime is again irreducible, okay. So f alpha and f alpha prime, these are associates in qx. So since this is irreducible associates of qx, so certainly f alpha prime divide g in qx, okay. But since this is a primitive polynomial, so therefore f alpha prime must divide g in zx as well, okay. So therefore what is the lesson? The lesson is that and okay, so and fine. So that also gives us another this also has some another implication. So therefore anyway g is having leading coefficient 1, okay, and I don't know about the leading coefficient of f alpha prime, but however since it divides g in zx, so that shows the leading coefficient of f alpha prime is a unit of f alpha prime is an unit. Hence like since this is an unit in of course unit in z, that is plus minus 1. So hence we can like by further modification we can consider f alpha prime to be a monic polynomial. So the upshot here is, so if alpha is an algebraic integer, alpha is of course an algebraic number and its monic polynomial and its monic and its irreducible polynomial has, and its irreducible polynomial is, so like by after multiplying by this unit f alpha prime, that will be monic and again irreducible. So therefore that is going to be equal to f alpha because of the uniqueness, hence f alpha will be monic and having coefficients in so just a minute, so f alpha prime, so f alpha prime is again going to be an irreducible polynomial. So it's an irreducible polynomial in by our construction, irreducible polynomial in qx as well. It has to divide this f alpha and like this f alpha prime multiplied by some unit, that will be an again irreducible polynomial in qx as well, because of again this from our construction this was an irreducible polynomial in qx and irreducible polynomial in qx, and it's also primitive by assumption, so it will be reducible in zx as well. So like therefore from this we immediately obtain that this f alpha will be some unit times f alpha prime. So that forces that f alpha is having all coefficients in zx. So its irreducible polynomial is has coefficients from Z. Okay. I hope the argument is clear. This is just a kind of division argument. For example, if you say so the like here it satisfies the polynomial x square minus 2, okay, and this exactly becomes the minimal polynomial of root 2 over q. And whatever we have done here, that can also be generalized in the following manner. So I am leaving that to you, that suppose you start with some integral domain, you consider its field of fractions and then take any extension of that, take an algebraic element from that extension. If so, the from algebraic element, if that is integral over the integral domain. So okay, let me put it in this way. So what I am saying is, whatever we have done there also admits an immediate generalization. So more generally, suppose R is an UFD, F is a field of fraction, K is an extension of that, alpha belongs to K, is integral over R. R implies alpha is algebraic over K F, and the minimal polynomial has coefficients from R. Okay, the same proof goes on. All right. So these are common examples of algebraic numbers. Further examples are, of course, this several roots of unity. So these are all algebraic numbers. So for our purpose, it will be enough to stick to the subfields of C. So like any subfield of C automatically contains Q, so it can be regarded as an extension of the field of rationals. So since for our purpose it will be enough to stick to subfields of C, so which are automatically regarded as Q's the extension of field of rationals. Therefore, the examples that we have given mostly those are the examples of algebraic numbers. So, but of course, you do have other general field extensions where the fields need not be contained inside C, and you can talk about algebraic elements there as well. But again, I don't want to spend time on giving examples of such things, because for our purpose, so for the sake of this course, what we just care is just the setup when we are working with subfields of C. Okay. So as I said, more general examples you can, more varieties of diverse examples you can see if you read the chapter of the first few chapters, if you read the first chapter on extension of fields from any algebra book, but I won't get into that. Okay, and also let me also give you some examples of algebraic extensions. As I said, we will stick to the situation when K is Q, unless otherwise required. So this, of course, this is a finite extension. So Q over Q is an extension of algebraic, is an example of algebraic extension. Similarly, this is an algebraic extensions. So again, let me remind you that by an algebraic extension, I mean an extension whereas every element is algebraic over the bottom field. Okay. Now let's talk about embeddings. So as I said that from now on, we will restrict our attention, we will focus our attention to the subfields of C only. But however, what the results that we will prove, most of them, perhaps in fact the verbatim repetition of the proofs that will be given, those proofs also work for arbitrary finite separable extensions. So if you are interested, you can you are invited to develop them in that generality, but for the purpose of this course we will stick to the subfields of C only, where the things are less technical and simple. However, as I said, that essentially all the main ideas. Okay. So, I will first talk about embeddings. So, till this point you see the things were pretty much analogous to that of integral dependence, but from this point onwards things will start, be different. So, suppose we are given two fields K and L. Here also I do not need to actually assume that these are subfields of C, just two fields, and let phi be a homomorphism from K to L. So, since K is a field, kernel phi has exactly two options, right? Kernel, so it is either the kernel being an ideal of a field, it has easily two options, either it is trivial or whole of K. Whole of K means that will force 1 to go to 0, but in a field we deliberately assume that is you have 1 is not equal to 0. So, therefore, this forces kernel phi is trivial, that is phi is injective, okay, phi is injective. So, in that case, so since we are dealing with now an injective homomorphism, so that then this phi k is a subfield of L, is a subfield of L. So, in that sense, so therefore, you can regard L as an extension of, so 1 right. So, phi k is isomorphic to K. So, since phi k is a subfield of L, so like L has a subfield, L has a copy of K inside that. So, in that sense you can regard L as an extension of K as well, of K, let me put it in this way, phi k, okay, yeah. So, by an embedding of K in L, I mean a homomorphism from K to L, okay. Since these are fields, automatically it will be an injective. So, I repeat, by an embedding, by an embedding of K inside L, I mean a homomorphism from K to L, of course, it will going to be automatically injective, okay. Some examples of embeddings. So, we do have very natural things, right. For example, let us say Q, the standard inclusion of Q inside R, or QR inside C, or Q inside C, or this Q root 2 or Q omega inside C. So, these are the rather the most easy examples of embeddings. I will give you another different example of embedding. So, suppose here we do have any field, let K be any field, and so Fx be an irreducible element, So, from this PID we obtain that this is a field, right, is a field, and now we have the following embedding sending each K to each alpha to alpha plus Fx, okay. And of course, this is a homomorphism, this is a field. So, this is so of course, this is a homomorphism because K is already contained inside Kx, a natural inclusion. So, this is an example of embedding, and the reason for giving this example is we will use this example in our discussion later on, okay. So, we have given some examples, though they are quite easy, some easy examples of embeddings. Now, we will talk about how embeddings behave with conjugates. So, for that first let me define the notion of a conjugate. So, like here from this point I will of course, some of them, as I said, might be generalized, but for our simplicity, from this point we always from this point onwards, all the fields that are going to appear will be, unless otherwise stated, will be subfields of C. So therefore, like suppose K is a subfield of C, a complex number C alpha. Suppose this is algebraic over K, it's algebraic over K, it's algebraic over K. Therefore, we have an irreducible polynomial. This is 0. Okay. So the like the and alpha. Okay, let me do it. Del f alpha be the irreducible polynomial of alpha over K. Okay. So the roots of f alpha. So roots means the complex roots. Roots need not lie in K, are called the conjugates. Conjugates of alpha over K. Okay. Sometimes we write over K. So thus, given an algebraic element over K, its conjugates are the roots of the all the other roots of all the roots of its minimal polynomial. For example, for root 2, its conjugates are root 2 and minus root 2. The conjugates of I are I and its complex conjugate minus I. Okay, and here also let me here also give another embedding example of an embedding from C to C. Of course, we have identity as an embedding, but we do have another embedding as well, complex conjugation. Okay. So this is another example where this is another embedding which is not just some sort of identity. Yeah. So let's come back to this. So so as I have just given some examples of conjugates of some elements. Now we are going to see how conjugates behave under embeddings. Okay. So let K be a subfields of C and sigma be an embedding of K inside C, and let alpha be an algebraic element over K whose minimal polynomial is f. Okay. Let me write f as n, so this is a x to the power n plus a n minus 1 x to the power n minus 1 a1x plus a naught. Okay. So the thing is that under the embedding, so if we call it f, so we let's define sigma f to be this polynomial. So x to the power n plus sigma a n minus 1 x to the power n minus 1 sigma 1 sigma a1x plus sigma a naught. Okay. Good. So denote the image of K under the embedding by K prime. So therefore sigma is an isomorphism between K and K prime, and as I have already seen that extends to an isomorphism from Kx to K prime x. Extend sigma to an iso from Kx to K prime x. Okay. And under this isomorphism f, this f maps to sigma f, right? and from this it immediately follows kx modulo. So, there is an isomorphism from kx modulo okay, let me put it in this way. Okay, there is an isomorphism. Of course, this sends x to x. All right. Now, tell me that so if this is the case, then what happens to alpha? Where does alpha go? So, first of all, alpha is one thing is clear, that alpha is a root of this polynomial. So, that means so alpha to the power n plus plus plus, this is going to be 0. I will directly substitute 0, right. If you apply, so this is an this is some is 0, and yeah. Let me now do the following, that if alpha is that, okay, alpha is there. So, alpha is algebraic over k. So, suppose that, so this is a very crucial observation. Suppose that let me do sigma prime is an extension of the embedding sigma to k alpha. Okay. So, therefore, sigma prime is a homomorphism from alpha this to c, and sigma restricted to k, sigma is sigma. Okay. So, therefore, once we apply, so this quantity is now perfectly, this the left hand side, this quantity lies in k alpha. So, therefore, once we apply sigma prime onto this, what do we obtain? We obtain the following, that so sigma prime alpha to the power n. So, we are dealing with since homomorphisms. So, sigma prime of n minus 1 times sigma prime of alpha to the power n minus 1, but in view of this, since sigma prime extends sigma, so therefore we have, okay, oh sorry, this will be rather sigma of n minus 1, I am sorry, sigma of a naught, and that is going to be 0. So, therefore, we see that sigma prime alpha is a root of this polynomial sigma fx. Okay. So, the observation is that suppose we have an embedding and an algebraic element. If this embedding has an extension, then under this extended embedding, this will go to, so this will go to some root of the image polynomial. Okay, that's what the general observation that we have used, and now that will culminate into the following observation. So, what is that observation? Let us look here. So, in this scenario k alpha is isomorphic to kx fx. We have an of course we have a isomorphism which sends x bar to alpha, and from here we have this isomorphism that also sends x to x, I mean x bar to x bar. Okay, this also is x bar to x bar, but here this well, I should not say x bar here, x plus fx to x plus sigma f or sigma f of x. Okay, and let beta be any root of, so this is a polynomial in C, so you can talk about any complex root of sigma of fx. Okay, let this be a root of sigma of fx, and certainly we also have another isomorphism between this and k prime beta, which is of course inside C, and this isomorphism sends x to beta. Okay. Now we just compose all these isomorphisms, that gives us an extension of k alpha, right. So try to again understand that in this scenario, suppose alpha is, since alpha is an algebraic over, assume alpha is algebraic over k. Now if we take any other root beta of this image polynomial, then we do have an embedding of k alpha into C. So try to see that like this embedding that fixes, so every element, if you take any element, let us say any element r from small k, so r from small k goes to r plus fx, that goes to this, because both these two embeddings that in some sense fixes. So let me write it, r from this goes to r plus this, again r plus this, and that again r. So try to understand the scenario that given this, now for every root beta of sigma f, we have an embedding of k alpha to this. Okay, let me write it much more neatly. So I think I should write it over there directly. I just can extend this thing. Our observation is the following, that shows, so alpha is an algebraic over k minimal polynomial this, then for every root beta of every complex root beta of sigma fx, there is an extension, there is an extension of this embedding, because like sorry, so it will be sigma r, because this is the extension of sigma at the level of polynomial rings and its quotient, sigma r plus this, yeah. So this is sigma r. So this clearly shows that this, I mean this isomorphism, so it fixes this isomorphism, extends. So the so try to again understand, we do have the following thing. Earlier we had k alpha over k, and from k to k alpha we have this isomorphism, and on which I also have, so we have an isomorphism that extends this sigma. Okay. So for every beta of root beta of this, there is an extension of sigma to k alpha that sends alpha to beta. Okay. So now you see that that gives us something very interesting. So so if this minimal polynomial has degree n, suppose degree of fx is n, then similarly degree of sigma fx will also be n. So therefore we have n such choices for beta. So therefore sending alpha to each of these beta, so you have n such betas, that gives us n such extensions. Okay. Thus this sigma has at least n extensions. So n is nothing but the degree of this thing. So as at least extensions to k alpha. Okay. Right. And furthermore, what we have observed here, that if sigma prime is an extension, then sigma prime must send alpha to some beta, where beta is the root of this sigma f. So therefore earlier we see that like sending this alpha to all these betas, we have n such extensions, and any such extension must send alpha to beta. So thus we and another thing is also quite obvious, that like from k alpha to k beta, suppose two extensions they agree on alpha. Suppose like we do have, okay, let me again put it in this way, you can immediately see. Suppose we have two extensions sigma 1 and sigma 2 of sigma, such that sigma 1 alpha equal to sigma 2 alpha, then that will imply sigma 1 equal to sigma 2, right? Because here the elements are polynomial expressions in alpha. Okay. So sigma 1 of alpha will be same as sigma 2 of sigma 1 of that polynomial expression will be same as sigma 2 of that expression, because both extend sigma and they agree on alpha. So therefore in view of all this, we now see sigma has exactly n extensions. Exactly these many extensions to k alpha. So let me summarize what we have seen, that suppose we are given an embedding of k inside C, then if you take an element, algebraic element k, alpha over k, then this extension can be extended to that of k alpha, an extension that of k alpha in exactly these many ways. Okay. We did it step by step. So first we proved that if any extension must send alpha to some root of this, okay, and then we proved that for any such any root here we do have an extension, and if two extensions of sigma agree on alpha, they must be equal. So now putting everything together, we have exactly these many extensions, and this can be moved further. How? So you see this, that this can be extended further. So suppose, so the scenario is exactly this k is a subfield of C and sigma is an embedding. And L is a finite extension. Yeah, so L subfield of C, finite extension. a finite extension, then sigma can be extended to an extended to an embedding, extended sigma admits sigma has these many extensions to an embedding of L. Clear? This exactly, it can be extended exactly these many ways. Why so? The proof is by induction. The proof is by induction because simply that L, since a finite extension, so we first join an element outside K. If this is equal to F alpha, then we are done. Otherwise, we take another element from the outside. So, like from the outside. So, like what I am saying is, we can choose elements alpha 1, alpha 2 such that is going to be L. Right. I told you the procedure that you first find something from outside K. If L contains K properly, if that becomes L, we stop, otherwise we take something from the outside, and in each step you see the vector spaces, the dimension is increasing, and therefore it cannot go indefinitely. And then the argument I would like, the rest of this argument I would like to leave it as an exercise, that the sigma can be extended to K alpha prime in these many ways, K alpha prime in these many ways, and each of these extensions can be further extended to this in these many ways. So that is how finally we will come, and then by the product formula that we have proved, this will be exactly this. Okay. And also you have to ensure that any extension of sigma to L must be one of these, and that is an easy task. Okay. If you take any extension of let us say some tau of sigma, then first of all the restriction of tau to K alpha 1 will be one of these. Okay. So then certainly the restriction of this tau to this will be the extension of what we have just considered here. So in that manner you can see that any extension must have been considered in this in this process. So that shows that this has exactly n extensions, and exactly number of extensions equals to the degree of the extension. Okay. And as an immediate corollary, we obtain the following. As an immediate corollary, we say the following, that let L and K subfields of C, and L is an extension of K, finite extension. Okay. Now as sigma we take the non-natural embedding. So there exists then there exist precisely these many embeddings of L that fixes K. Embeddings of L fixing K pointwise. So, what you do is you take sigma to be the, as I said, the natural inclusion, and that extends to an embedding of L in these many ways. Okay. So, look at this corollary that given any extension of subfields of C, there exist exactly these many embeddings of L which fixes K pointwise. Okay. Now, we are about to define an important notion, a very special type of fields extensions. They are called normal extensions. So, definition. So, as expected, we have an extension of subfields of C, finite extensions. Okay. So, first this extension is said to be, or L is said to be normal over K, if it satisfies one of the following, one means equivalently all, one of the following statements or following conditions. What are the conditions? L is closed under taking conjugates over K So, what it means is, that is, for every alpha in L, all conjugates of alpha over K lies in L. Okay. The second condition is every embedding of K, every embedding of K embedding of L fixing K pointwise is an automorphism of L. Automorphism of L. Why so? I will give a quick proof of that. I will give a very quick proof of that. So, one of them will be actually trivial, because because let us say, okay, so let us try to prove 1 to 2. 1 to 2. So, so if this is an embedding of L, if this is an embedding of L to C fixing k, small k, for each small k belonging to capital K, we have to show that like sigma of L is contained inside L. Okay. So, since sigma of L contained inside L, then sigma of L will have if I said it suffices to show this. Okay, this is because like degree. So, since k sigma fixes k, so this will be okay because of so whatever then since this fixes k, so then any embedding can be regarded as a linear map, and here it will be an injective linear map. So, this has same dimension over k as that of L. Now, since this is, if we can prove this, then since both are finite dimensional, one will immediately obtain that sigma L equal to L. So, now we have to show this, and how to show this? That's quite simple, that if you take any alpha in L, so if you take any alpha in L, so alpha will have some minimal polynomial f, okay, and therefore you see sigma of f, since sigma fixes k, will be f itself. So, we have already observed that, so the root sigma of alpha has to be a root of sigma of fx, okay, which is fx. So, therefore, sigma of alpha will be a conjugate of alpha. Sigma alpha is a conjugate of alpha, since alpha is closed under taking conjugation, this forces sigma of alpha belonging to L as well. Okay. So, then here the main observation is that any homogeneous embedding that fixes k can be regarded as a linear map from L to C. All the vector spaces are regarded over k, so injective linear map. So, therefore, this will have same dimension as that of this over k, and since everything is finite dimensional, once we can show this, it will be immediate the sigma L equal to L. So, the 1 goes to 2 is fine, to show 2 goes to 1, that is also not difficult, because let alpha is in L and let beta be a conjugate of alpha, we have already shown that we do have an extension, that fixes k pointwise, right. So, you just take the identity mapping, this natural inclusion of k in C, and that extends to extends to this isomorphism, which is of course an embedding of k alpha, right, and then we can further extend. I am just explaining the proof orally, or maybe I can write, extend this further, to an embedding of L. Okay. Since this fixes k pointwise, this extension will also fix k pointwise. Okay. It is an embedding of L into C, of course, and this embedding sends alpha to beta, which is a conjugate. Now, since any such embedding is an automorphism of L, therefore, it will follow from to that so that will follow from that beta will also belong to L, because beta is the image of the embedding, this embedding that sends alpha to beta, right. From 2 it follows that beta will also lie in L. So thus it shows that it's closed under taking conjugates. Yeah. Now we will just finish with one simple corollary. So the corollary is that suppose L is k alpha n up to alpha n, all these are algebraic, and L contains all conjugates of alpha is, then L over k is normal. Okay. For example, a special case which we will use, special case q over this nth root of unity is a normal extension, because all conjugates are some powers of omega. Now how to prove this? This is just a one liner proof, and with that I will finish. So so what's the typical element here? It looks like a polynomial in the variables, polynomials in this alpha n up to alpha n, okay, and coefficients are coming from k, okay. So now if we consider any embedding, let sigma be an embedding fixing k, then once we apply sigma on this object, then what will we obtain? The coefficients are not going to be changed, and alpha i's are being sent to its conjugates, but conjugates are already inside L. So therefore this object will lie inside L. So thus you see that any embedding of L sends a typical element here to inside L as well. So therefore in view of this we obtain that this is normal. Okay. So I think with that I finish all whatever I need from the theory of field extensions. But as I said that I have done it for finite extension of subfields of C, but whatever I have done that generalizes to arbitrary finite and separable extensions. Okay, so with that I will stop.